The universe is a tremendous and secretive scope loaded up with peculiarities that challenge how we might interpret space-time and the actual idea of the real world. Among the most puzzling of these peculiarities are dark openings, vast Goliaths that consume everything in their way, including light itself. These heavenly objects, brought into the world from the leftovers of enormous stars, have gravitational powers so strong that they twist the very texture of existence. With the coming of cutting-edge innovation, especially the James Webb Space Telescope, JWST, researchers are starting to uncover new insights into these strange substances, reshaping how we might interpret the universe. Dark openings are not simply standard divine objects. They are regions of space where gravity is so serious that nothing, not even light, can escape their grip. This makes them extraordinarily hard to straightforwardly notice. The most gigantic of these, known as supermassive black holes, are found at the centers of galaxies and can have masses ranging from millions to billions of times that of the Sun. Their beginnings and development are subjects of intense study and debate among astronomers. These supermassive black holes are believed to have formed from the remnants of dying stars. However, the specific course of their development remains one of the great mysteries in astronomy. When an enormous star depletes its atomic fuel, it undergoes a disastrous breakdown under its own gravity, potentially forming a black hole if the mass is adequate. The resulting black hole continues to grow by accumulating matter from its surroundings, frequently forming a gradual accretion disk of gas and dust that spirals into the black hole, heating up and emitting intense radiation in the process. The very first image of a black hole, captured in 2019 by the Event Horizon Telescope, was a great accomplishment in the field of cosmology. This image provided the world with visual confirmation of the presence of black holes, specifically the supermassive black hole at the center of the galaxy M87, situated around 55 million light-years from Earth. This remarkable picture showed a bright ring of light surrounding a dark shadow, which is the event horizon, the point beyond which nothing can escape the gravitational pull of the black hole. This historic picture was not only a visual triumph but also confirmed many predictions made by Einstein's theory of general relativity. The successful capture of this image required the coordination of a global network of radio telescopes, effectively creating an Earth-sized virtual telescope. This achievement has opened new avenues for studying black holes and confirmed that these vast monsters are not just hypothetical constructs but real entities that play a critical role in the formation of galaxies. While the image of the black hole in M87 was a recent breakthrough, the quest to confirm the presence of black holes goes back much further. The first solid candidate for a black hole was Signis X1, discovered in 1964. Signis X1 is a stellar mass black hole, significantly smaller than supermassive black holes. Nevertheless, its discovery marked a turning point in the study of these objects. Found around 7,200 light-years from Earth in the constellation Cygnus, it is part of a binary system where it is paired with a massive blue supergiant star. The black hole's presence is inferred from the X-rays emitted as material from the companion star is pulled into the black hole's accretion disk. These X-rays, detected by early space-based observatories, provided the first solid evidence that black holes were not just hypothetical objects but real, observable phenomena. The discovery of Signis X1 was met with both excitement and skepticism among leading scientists, including Stephen Hawking and Kip Thorne. In 1975, they famously made a bet as to whether Signis X1 was indeed a black hole. Thorne, confident in the data, argued that it was. Hawking, more cautious, disagreed. As additional observations accumulated, the evidence for Signis X1 being a black hole became overwhelming, and in 1990 Hawking conceded the bet. This confirmed Signis X1 as a black hole and marked a significant milestone in black hole research. Despite the theoretical predictions and indirect evidence, detecting and studying black holes remains an incredibly challenging task. Unlike stars, black holes do not emit light, making them invisible against the backdrop of space. Researchers rely on the effects black holes have on nearby objects to identify them. This includes observing the motion of stars and gas clouds orbiting these hidden objects, as well as detecting X-rays emitted by material heated to extreme temperatures as it is pulled into the black hole. One of the main challenges in black hole detection is the need for precise and sensitive instruments. The X-rays and other forms of radiation emitted by black hole accretion disks are often faint and can be easily drowned out by other sources of cosmic noise. Moreover, the vast distances to many black holes mean the signals we receive are incredibly weak, requiring advanced technology and techniques to detect and analyze them. The advent of space-based observatories, such as the Chandra X-ray Observatory and the later James Webb Space Telescope, has significantly improved our ability to detect and study black holes. These observatories are free from the distortions caused by Earth's atmosphere and can observe the universe in wavelengths of light that are blocked by the atmosphere, such as X-rays and infrared. This has allowed astronomers to study black holes more closely and has led to numerous new discoveries. Launched in 2021, the James Webb Space Telescope, JWST, represents a new era in space exploration and black hole research. With its powerful infrared capabilities, JWST is designed to look into the distant universe, capturing light that has traveled billions of years to reach us. This makes it an optimal tool for studying the early universe and the formation of the first galaxies and black holes. One of the key advantages of JWST is its ability to observe in the infrared range. Infrared light can penetrate dust clouds that often obscure visible light, allowing JWST to reveal structures and objects that would otherwise remain hidden. This is especially important for studying the regions around black holes, which are often surrounded by thick clouds of gas and dust. JWST has already made several groundbreaking discoveries in its short time in operation. Among these is the detection of a large dormant black hole near our solar system, located within the Milky Way galaxy. This black hole, known as Gaia BH3, is the second closest known black hole to Earth and has a mass approximately 4 times that of the Sun. Despite its proximity, Gaia BH3 remained undetected until JWST and other observatories provided the critical data to confirm its existence. Gaia BH3 is situated in the constellation of OMA, around 1,926 light-years from Earth. It was discovered by accident as astronomers were analyzing data from the European Space Agency's Gaia mission, which is mapping the positions and movements of stars in the Milky Way. The discovery of Gaia BH3 highlights the capabilities of modern telescopes and the surprises that still await us in our own cosmic backyard. Gaia BH3 is classified as a dormant black hole, meaning it is not actively accumulating material from a companion star and therefore does not emit significant amounts of radiation. This makes dormant black holes particularly difficult to detect, as they do not produce the bright X-ray emissions typically associated with active black holes. Instead, their presence is inferred from the gravitational effects they have on nearby stars and other objects. The discovery of Gaia BH3 is significant because it provides astronomers with a rare opportunity to study a black hole that is not currently active. By observing the motion of stars orbiting this black hole, researchers can gain insights into its mass, spin, and other properties. This, in turn, helps us understand the life cycles of black holes and the factors that determine whether they are active or dormant. Dormant black holes like Gaia BH3 are believed to be relatively common in the universe, but they are challenging to find. The discovery of Gaia BH3 so close to Earth suggests that there may be more dormant black holes lurking in our galaxy, waiting to be discovered. One of the most exciting aspects of the JWST mission is its ability to study the early universe and the formation of the first black holes. The early universe, just a few 100 million years after the Big Bang, was a period of intense activity, with the first stars and galaxies forming from clouds of gas and dust. It is during this time that the first black holes are believed to have formed. However, the details of this process remain shrouded in mystery. Recent observations by JWST have provided tantalizing glimpses into this distant past. One of the most significant discoveries is the detection of an incredibly red supermassive black hole in the early universe, located about 12.9 billion light-years from Earth. This black hole, estimated to have a mass of around 40 million times that of the Sun, is among the earliest and most massive black holes found so far. The discovery of this red supermassive black hole challenges existing models of black hole formation and growth. The fact that such a massive black hole existed less than 1 billion years after the Big Bang suggests that black holes can grow much faster than previously thought. This raises important questions about the processes that drive the rapid growth of black holes and how they interact with their host galaxies. The discovery of supermassive black holes in the early universe also brings up a fundamental question in astronomy. Did black holes form first, or did galaxies form first? This is often referred to as the chicken or egg problem in cosmic evolution. The study of black holes not only enhances our understanding of these enormous phenomena, but also drives the development of new technologies and techniques. As astronomers push the boundaries of what we can observe, they are continually developing more sensitive instruments and innovative methods. These advances help us probe the extreme conditions near black holes and gather more detailed information about their properties. One exciting area of research is the study of gravitational waves, ripples in spacetime caused by massive objects like black holes merging. Detectors such as LIGO and Virgo have already observed several black hole mergers, providing crucial information about their sizes, frequencies, and the nature of these cosmic events. The ability to detect and analyze gravitational waves offers a new way to study black holes and test theories of gravity. As observational technology continues to improve, future missions and telescopes will further refine our understanding of black holes. Upcoming projects, such as advanced space observatories, are expected to provide even deeper insights into the behavior of black holes and their interactions with their surroundings. These advances will likely uncover new aspects of black hole physics, including their role in galaxy formation, the nature of their interiors, and their ultimate fate. In conclusion, the study of black holes is a dynamic and rapidly evolving field that continues to captivate scientists and the public alike. Each new discovery pushes the limits of our knowledge and reveals more about these enigmatic giants. As technology and research techniques advance, we can expect to uncover even more about the true nature of black holes and their impact on the universe. As we delve deeper into black hole exploration, scientists are also investigating the theoretical implications of these discoveries. The mysteries of black holes challenge our understanding of fundamental physics, especially the reconciliation of general relativity with quantum mechanics. One key area of interest is the information paradox, which questions whether information about matter that falls into a black hole is lost forever or if it can be recovered. This debate addresses the very fabric of reality and how information is preserved or destroyed under extreme conditions. Additionally, the study of black holes offers crucial insights into the nature of dark matter and dark energy. By observing how black holes influence their surroundings, scientists can infer the presence of these elusive components of the universe. This could help answer some of the most profound questions in cosmology about the structure and fate of the universe. Furthermore, as our observational capabilities grow, black hole research could uncover new types of black holes, or even entirely new phenomena. For example, intermediate mass black holes, which are between stellar mass and supermassive in size, remain elusive but could offer new insights into the formation and evolution of black holes. Similarly, the potential discovery of primordial black holes, formed in the early universe, could shed light on the conditions of the early cosmos and the formation of the first galaxies. In essence, the ongoing study of black holes not only expands our understanding of these cosmic giants but also pushes the boundaries of how we understand the universe as a whole. Every discovery leads to more questions and fuels the quest for answers, ensuring that the study of black holes remains one of the most fascinating and transformative fields in modern science.